Hello everyone. Today we are going to start a new chapter which is known as convection. We know conduction. Uh, Conduction is the mode of heat transfer in which heat is transferred due to the property of the material to allow the passage of heat. We know conduction. And we also know that conduction requires solid medium. In conduction, two factors are responsible for the transfer of energy through the solid. One is due to atomic vibration, second is due to availability of the free electron. We know all these things. Now, what is convection? Convection is the mode of heat transfer in which heat is transferred due to the heat carrying capacity of the molecule. Let's say it's a wall. This wall is in contact with the fluid. There is a temperature difference between the surface of the wall and the temperature of the fluid. Let Ts is the surface temperature and Tf is the temperature of the fluid. Now the heat transfer due to the heat carrying capacity of the molecule from one place to another place, or from the surface to the fluid, or from the fluid to the surface due to movement of molecule, is known as convection. We know convection is of two types. First one is natural convection. Natural convection is also known as free convection. It is also known as free convection. Second is a forced convection. These are the two modes of convection. We know that what is natural convection. We know that what is forced convection. Natural convection is the mode of heat transfer in which heat is transferred from one place to another place due to the movement of molecule. And movement of molecule from one place to another place, it is due to the temperature difference only, due to density difference only, due to density difference or temperature difference. In case of forced convection, the heat transfer is again due to movement of molecule from one place to another place, but in this case movement of molecule takes place due to with the help of some external source, with the help of some external energy, as example of a fan. Now the exchange of heat from the wall to the fluid, from the wall to the fluid, or from the fluid to the wall is very important process in heat transfer. It presents this type of process, heat transfer process presents in all types of heat exchangers, and it plays an important role in the operations and performance of engines and many more mechanical equipments. To evaluate the rate of heat transfer, in case of convection, to evaluate the rate of heat transfer, there is an equation given by the Newton cooling law that is known as A H T surface minus T fluid, where A is the area perpendicular to the direction of heat flow, H is the convective heat transfer coefficient, and Ts is the surface temperature or wall temperature, Tf is the fluid temperature. This equation it looks very simple, or we can say its simplicity may mislead, or it is deceptive, because it looks simple but this process is very complicated. In this case, the convective heat transfer coefficient is actually a complicated function. This convective heat transfer coefficient is a complicated function of fluid flow, thermal property of the fluid, geometry of the system, and its numerical value is not uniform over the surface and depends also on location where the fluid temperature is measured. So we can say in convection we are interested to find the value of heat transfer coefficient H, which itself is very complicated. It depends upon number of factors. Although this equation, which is a Newton cooling law, is used to determine the heat flow by convection from the surface and or you can say from the fluid to the surface to fluid, but this relation is we can say it is inadequate It is inadequate to explain the convective heat transfer mechanism. Why it is inadequate? Because to we should have knowledge of a one more subject which is known as fluid dynamics, or the nature of the fluid flow. We have already done this fluid mechanics in our engineering courses. We know what is ideal fluid. We know this what is ideal fluid. We know what is viscous fluid. We know all these things. We know uh, what is stream function, what is potential function, what is the difference between these two, and how to derive the we can say there is a equation which is known as a continuity equation. We have already done these types of derivations in fluid mechanics, and we also know that what is the difference between laminar flow and turbulent flow, and this can be explained with the help of a very important uh, experiment that is known as Reynolds experiment, which gives the non-dimensional number Reynolds number. Reynolds number, we know Reynolds number is a dimensionless parameter, is a number which is the ratio of two forces, inertia forces to the viscous forces, inertia force to the viscous force, or its formula in the form of rho dV upon mu, where these are the properties of the fluid. Rho is the density, d is the characteristics dimension diameter, v is the velocity, and this is the viscosity, rho dV upon mu. Then we are interested to do the dimensional analysis and model testing. We are interested to do, let us start. The next topic is the dimensional analysis. In dimensional analysis is a mathematical technique, or we can say mathematical model. It's a mathematical method for obtaining the certain type of equations. With the help of dimensional analysis, we find few equations. Those equations govern some natural or physical phenomena, and by balancing the fundamental dimensions, we know there are fundamental dimensions. By balancing those fundamental dimensions as mass, length, and time, and temperature, then there is a one more fundamental dimension when we are dealing with the heat transfer, that is temperature. By balancing these fundamental dimensions, the problem which we will consider, which is a physical phenomena or a natural phenomena, we can derive the relation for that. The method can be applied to all type of fluid resistances, all types of heat flow problems. We can apply this method to fluid flow problem. We can also apply this method to heat transfer problem, and equations are produced. Those equations are in the form of non-dimensional numbers, and these non-dimensional numbers are very important in engineering practice. We are interested to find the non-dimensional numbers. What are these non-dimensional numbers? We are going to do one by one, and those non-dimensional numbers are used to derive the relation. They will be used in the relations. And the heat lost by convection, whether it is a natural convection or a forced convection, heat lost is extremely complex phenomena. It's a very complicated process. and it involves various controlling variables, it is very difficult to study the effect of each variable on, on the process. It is possible to investigate experimentally. It is possible to investigate experimentally and to express scientifically the result of any one geometrical configuration using the dimensional analysis. By using this dimensional analysis for each configuration, next we have to do the criteria for similitude. Criteria for similitude. What is this criteria for similitude? We know due to the complexity of the law of fluid motions, it has been possible to solve analytically only the relatively small number of practical problems of the fluid mechanics and heat transfer. We can deal with the small numbers. But when the numbers are more, it is necessary to do the experimentation on the models and predicting the behavior of the original from the result of the test model. A good knowledge of the law of similitude is required for the planning and for the interpretation of the model experiment. Generally, we will concern with the three types of similitude. There are basically three types of similitude. First one is the geometrical similitude. Second is a kinematic, and third one is a dynamic. Second is kinematic and third one is a dynamic similitude. These are the three types of similitude. Geometrical similitude is the similitude of shapes and geometry. Two objects are said to be geometrically similar if their ratios of homogeneous dimensions are equal. Kinematic similitude means two motions. This is related to the kinematic similitude is related to the motion. Two motions occurrences are kinematically similar. We can say two motions are kinematically similar if the patterns or path of the motions are geometrically similar for this case. Third one is the last one, which is a dynamic similarity or dynamic. In this case, this is the similarity of forces. Two motions, when there are two motions and they are dynamically similar, if the kinematically similar, there should be a kinematical similarity, kinematically similar, and if ratios of homogeneous forces in the system are same. So the forces is proportional to the mass times acceleration. We know that mass into acceleration. We know the similarities. Our next topic is Buckingham pi theorem. We know what are the various types of similarities like geometrical similarity, kinematic similarity, and dynamic similarity. We will do the Buckingham pi theorem and we will use those similarity while deriving the relation. What is Buckingham pi theorem? According to Buckingham pi theorem, if there are n variables, let's say there are n variables, and they are influenced by some phenomena, maybe a phenomena, maybe convection, maybe a natural convection or a forced convection, and if they can be expressed by m primary dimensions, primary dimensions like mass, length, time, and temperature. These are the primary dimensions. And the dimensionless independent group formed will be, for that case, dimensionless group formed will be n minus m. There will be n minus m pi terms. They are also known as pi terms. The dimensionless terms are called pi terms, The independent dimensionless group can be rearranged. We can say pi 1, pi 2, pi 3 may be number of pi terms is equal to 0 in a particular phenomena, maybe a convection, natural convection, forced convection. Let's say in any phenomena involving 7 variables, let's say any phenomena involving n is equal to 7, and in that case there are primary dimensions m, let's say it is 4, then pi terms will be n minus m, which is 7 minus 4 will be equal to 3. Or we can say for that case f will be equal to pi 1, pi 2 and pi 3 will be equal to 0. Each dimensionless pi term is formed by m variables, and along with one selected remaining n minus m variables, and pi terms involve m plus 1 variables. The m variables equal to primary dimensions formed in a core group. It is also very important when pi terms are formed, then one pi term can be expressed as a function of remaining pi terms. The formed pi terms can be represented in terms of multiplications or division of the pi terms, but not in addition or subtraction. What is the meaning? We can say the formed pi terms can be represented in the terms of multiplication or division. For dimensional analysis, when we apply the Buckingham pi theorem, we have to decide what are the repeating variables and what are the non-repeating variables. There are two types of variables. We will repeat a few variables, those are known as repeating variables. Remaining will be non-repeating variables. Each dimensionless pi term is formed by m variables, we know, along with one selected from n minus 1. We will select one from n minus 1 variables to form each pi terms. These m variables, we have considered these m variables formed a core group which appears repeatedly in pi terms. When we will derive, that core group will appear repeatedly in pi terms, and those variables which are in that group are known as repeating variables. The repeating variables are selected among the n variables. From the out of n variables, we have to select repeating variables which will form the group, and they are selected in such a way that they together must not contain primary dimensions. The first point is they must not contain primary dimensions, and the second one, they themselves must not form a non-dimensional numbers. The second condition, they must not form a dimensionless group themselves. As far as possible, the dependent variables should not be selected as repeating variables, and the final one is no repeating variable should have the same dimensions. The repeating variables should be chosen in such a way that one variable contains geometrical property, the other contains dynamic, and the we can say the remaining contain the dynamic similarity. We have to choose the repeating variables in such a way that one variable contains geometrical property, the other contains dynamic properties. Next topic is when we will consider the forced convection, how to apply the dimensional analysis on a convection phenomena which is a forced convection. We will use the Buckingham pi theorem for that. For finding the heat transfer coefficient, the following factor can be considered for the case of forced convection. If H is the heat transfer coefficient, it will be a function of various other terms like rho density, characteristics length, velocity, kinematic viscosity. Cp is the specific heat, and K is the thermal conductivity. We can say there are 1, 2, 3, 4, 5, 6, 7. There are 7 variables. We can say N is equal to 7. Now there are 4 fundamental dimensions. We know M is the fundamental dimension. There are 4. How many pi terms will be there? Pi terms. How many pi terms will be there? 7 minus 4 means 3. There will be 3 pi terms. Let's say they are pi 1, pi 2 and pi 3. These are the 3 pi terms which we will find by applying the dimensional analysis for forced convection. We can write down the equation. F, we can say, is a function of pi 1, pi 2, pi 3, which is equal to 0. According to Buckingham pi theorem, we can say, let's say, write this equation again. H rho L V U C P K is equal to 0. 1, 2, 3, 4, 5, 6, 7. These are the 7 variables. Or we have to choose repeated variable to form a core group. We are interested to find the repeated variable for core group. I'm going to mark those variables H, rho, L and V. These are our repeated variable to form a core group. These variables will repeat for every pi terms, for pi 1 also, 2 also and 3 also. Now according to Buckingham pi theorem, these marked terms H, rho, V, L and V velocity, these marked terms contains 4 fundamental dimensions according to the theorem. The problem can be solved by 7 minus 4, 3 pi terms, we know. Now fundamental dimension must form a non-dimensional group with each remaining are mu, Cp and K. We will consider the remaining with the core group for, let's say we will consider pi 1. First of all consider mu, the remaining, and the core group H, rho, L and velocity. We will write down A, B, C and these are the power of these variables, and we will equate this equation with M0, L0, T0 and let's say theta is for temperature, theta or small theta 0. When we will solve this equation equating the power of M, L, T and theta, we get the equation for pi 1. Pi 1 will be equal to mu upon rho, L and V. After simplification and rearrangement by solving the above equation by putting the various dimensions, when we will solve that, we get the value of pi 1 which will be in the form of mu upon rho, L and V. Rho, L and V. Similarly, we can find the equation for pi 2 and we can find the equation for pi 3. For the case of pi 2, here the value of mu will change. This is the repeated variable group, core group. This here the Cp will come instead of mu for the pi 2. For the pi 3, in place of mu there will be K. We will follow the procedure. The procedure is same to find the value of pi 2 and pi 3. For the case we know, when we will solve the equation by equating this equation with M0, L0, T0 and theta 0, we find the equation which will be equal to pi 2. Pi 2 will be Cp rho and V by H, and pi 3 will be equal to, finally it is equal to K by HL. These are the 3 pi terms which are non-dimensional numbers by using the Buckingham pi theorem. Now we know pi 1, we know pi 2, we know pi 3 in the form of non-dimensional numbers, in the form of ratios. According to Buckingham pi theorem, according to Buckingham pi theorem, we can say that, let's say pi 3 is a function of pi 1 and pi 2. We can write down the equation in this form. After simplification and rearrangement, we will see h by k by hl will be equal to, after simplification I am going to write down the final equation. It will be a function of mu by rho lv. It will be in the form of, we can say, raised to power some constant, and mu cp by k in the form of, let's say, another constant m. Or this equation will be form of, where we know by rearranging and simplification, on the one side there will be Nusselt number, which will be a function of Reynolds number, which will be a function of Reynolds number raised to power something, let's say n, and second is the Prandtl number raised to power n. This will be our equation, final equation, which is required for the dimensional analysis, final equation, when we will apply the dimensional analysis for forced convection. Or we can write this again equation into the form of constant. Nusselt number will be equal to some constant Reynolds number raised to power n, Prandtl number raised to power m, where we know Reynolds number is a ratio of two type of forces, which is rho vl by mu. We know Nusselt number, which is a ratio of hl by h by kl, and hl by k, sorry, it's hl by k. Nusselt number will be hl by k, we know this, and Prandtl number is mu cp by k, mu cp by k. These are the formula for various non-dimensional numbers, and the value of these constants c n and m, they are constant. The value of these constant can be calculated experimentally. Similar procedure and similar method can be followed for the case of natural convection. If we are going to consider the case of natural convection, the phenomena is natural convection instead of forced convection, then again all steps will be same. We will follow various steps in the same order. We will choose first of all n number of variables. We will choose m, then we will apply the Buckingham pi theorem, then we will finally we will get the relation of non-dimensional number, and those that equation for the case of natural convection, the equation will be in the form of Nusselt number will be equal to constant Prandtl number raised to power, let's say, n, and there will be one more number, which is a Grashof number raised to power m. Our next topic is physical significance of various non-dimensional numbers like Reynolds number, Prandtl number, Nusselt number. What are their physical significance? First of all, consider Reynolds number. Reynolds number, and it is represented by symbol Re. We know Reynolds number is the ratio of two type of forces. We know that Reynolds number is the ratio of inertia force to the viscous force. Inertia force to the viscous force. IF is the inertia force, VF is, let's say, viscous force. It is the ratio of these two quantities. And in the form of formula, we know Reynolds number is the ratio of, in the form of formula, it is rho VL upon mu, where rho is density, velocity, length, and mu is the kinematic viscosity. We can convert this equation into the form of, let's say, this can be written into the form of rho v square upon mu v by L. We can convert this equation by simplification or by rearrangement like this. In this equation, the quantity rho v square, this quantity rho v square the quantity rho v square, rho v square. This quantity is a momentum flow. We know it is a momentum flow. It is representing the momentum of the flow. And the second quantity, which is this, which is mu v by L, it is the momentum flow through any tube per unit cross section area. And this is the quantity which is representative of shear flow. This quantity is a representative of shear stress. We can say it's the shear due to action of the viscosity. So when we want to understand the physical significance of this number, we can say it is the relative magnitude of inertia force, which is due to momentum. We can say inertia force to the viscous force. The higher the Reynolds number, the value of the Reynolds number, if higher it is higher, the higher the Reynolds number will be, we can say the greater will be the relative contribution of the inertia flow. And smaller the Reynolds number, the greater will be the contribution of, we can say, relative magnitude of shear stress. The next non-dimensional number is the Prandtl number, and it is represented by symbol PR. We know Prandtl number, it is equal to mu Cp by K, and it is also equal to nu by alpha, where nu is the dynamic viscosity and alpha is the thermal diffusivity. The physical significance of this number, Prandtl number, is that it signifies the relative speed of momentum and energy. Nu is the representative of momentum and alpha is the representative of energy, and it is the relative measure of these two quantities. It takes into account the three physical properties of the fluid at a time, mu, Cp by K, or we can say in the form of nu and alpha. And nu indicates the momentum transport. It indicates the momentum transport, and it indicates the thermal energy transport. And again we can say that it signifies the relative speed. It signifies the relative speed with which the momentum and energy are propagated through the fluid. The next one is the Nusselt number, and it is represented by Nu. We know Nusselt number is equal to HL by K. Heat transfer coefficient, characteristics length, and K is the thermal conductivity of the fluid. By definition, Nusselt number Nu is equal to, it is the ratio of heat transfer rate to the heat conducted under temperature gradient delta theta by L through the fluid. When we are comparing these two types of heat convected to the heat conducted, then we can say Nusselt number is equal to HL by K. How? If Q is the amount of heat, and we can convert this equation into the form of Q divided by delta theta L by K, which will be equal to, we can say, Q upon delta theta by K by L multiplied by K. This is the heat due to convection through the fluid, and this is the heat due to conduction through the fluid. Or by definition, again we can say Nusselt number is the ratio of heat transfer rate by convection to the heat conducted under temperature gradient delta theta by L. Next non-dimensional number is a Grashof number, which is represented by GR. By definition, Grashof number is the ratio of product of inertia force and buoyancy force to the viscous force square. When we will put the value of inertia force, buoyancy force, and viscous force in this equation, Grashof number will take the form of rho square beta g delta theta L cube divided by mu square, where rho is the density, beta is the expansion coefficient, thermal expansion coefficient of thermal expansion, g is the gravitation constant, delta theta is the temperature difference, and L is the characteristics length, and mu is the kinematic viscosity. This Grashof number, it is used in free convection. Its role is same as the Reynolds number in forced convection. We know for the case of natural convection, equation will be in the form of Nusselt number will be equal to Prandtl number and Grashof number. Equation will be in the form of Reynolds Prandtl number, and it's a Prandtl number, and it's a Grashof number. This Grashof number, it characterizes the types of boundary layer developed in the natural convection heat transfer. And we know it is very important in case of natural convection. It is an important non-dimensional number in natural convection. For a free convection, for the case of natural convection, transition from laminar, we know there is a transition from laminar to turbulent. There is a transition, and it occurs at when Grashof number is approximately equal to, we can say, 10 raised to power 9. It occurs at when Grashof number is approximately equal to 10 raised to power 9.